तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody. In our series of lectures on basic electronics, learning by doing, we will move on to the next. You might recall that we have been discussing over the past couple of lectures on the characteristics of operational amplifiers. You can see on the screen I have listed the different characteristics that we should normally worry about, namely input offset voltage, input bias current, input resistance, output resistance, CMRR common mode rejection ratio, and then transfer characteristics between the input and the output of the amplifier, gain bandwidth product, and finally the slew rate. There are a few more characteristics about which perhaps we will not go into the details, but you might also recall that several of these characteristics we have already discussed in our previous lectures, up to, for example, the common mode rejection ratio, and we also performed experiments to really measure these characteristics of the amplifier in the laboratory. Today we will try to discuss the transfer characteristics, the gain bandwidth product, and perhaps the slew rate of the operational amplifier. So what is the transfer characteristics? I had just few minutes during my last lecture where I explained about the transfer characteristics. I would quickly recapitulate what we discussed last time and try to go ahead further. The transfer characteristics corresponds to the input and output characteristics of the operational amplifier. So you can see on the screen you have an operational amplifier with the two input V1 and V2 corresponding to the inverting and the non-inverting inputs, and you have the output, and the V plus and V minus corresponds to the power supply. So because we all know by now that the operational amplifier is basically a differential amplifier, therefore the input voltage which is available between the two input terminals, the Vi, is nothing but the difference in voltage between V1 and V2. So the output voltage is equal to the gain of the amplifier, which I indicate here as AOL multiplied by the exact input voltage Vi, or in this case V1 difference V2. So this AOL is actually called the open loop gain, that OL means open loop. So this is the gain, open loop gain. That means what? We do not have any feedback provided in the amplifier. So then we call that as a open loop amplifier, open loop gain. So basically it is a linear amplifier, therefore output should be proportional to the input, and the proportionally constant is what we call the amplifier gain. So V output is equal to AOL multiplied by Vi. This is what we know. So, if I want to know now understand about the transfer characteristics of the amplifier, all that I have to do is vary Vi and look at what happens to Vo and draw a graph between Vi and Vo. That graph will correspond to the transfer characteristics between the input and the output. We know typically for an operational amplifier the open loop gain is about 10 power 5. For example, in the case of 741, which is the most popular operational amplifier, the value is close to 10 power 5 or 100,000, that is the total gain, open loop gain without any feedback. Now, if I give 1 volt differential input between the two inputs, then what will be the output? Going by the equation that I already gave you, V output is equal to AOL into Vi. So, that means 10 power 5 into 1 will be the output voltage. So, V output will be 10 power 5 volts, that is what you would expect. Can it be 10 power 5? No way, because in any amplifier the output cannot be larger than the power supply voltage that we have provided. So, it is the DC power supply which we are using, the energy from that power supply we are using to perform this action of amplification. Therefore, it is against all basic principles of physics that we can get an voltage which is much larger than what is the maximum voltage that we have in our battery or whatever. And therefore, if I give 1 volt, I will not get at the output 10 power 5 volts, but I will only get the maximum voltage that is possible to get from the amplifier, and the maximum is very close to plus Vcc and the minimum is close to minus Vcc. The Vcc in this case, if I assume to be plus or minus 12 volts, so you can see the output voltage can never be greater than plus 12 volts or minus 12 volts, irrespective of whatever may be the input I give. Therefore, the amplifier cannot be an amplifier for all types of input voltages. This is a very important idea. So, we can therefore try to look at what will be the range of input voltages for which I will get amplifier behavior, well defined amplifier behavior, which is characterized by the equation V output is equal to AOL into Vi, which I showed you already. So, similarly they have shown here, if I give minus 1 volt as the differential input, the output voltage will again be minus 12 volts, that will be the maximum that I can or minimum that I can get on the output. Hence, you see the output cannot be different from plus 12 volts to minus 12 volts. Anything beyond this limit of plus 12 volts to minus 12 volts is not possible at the output. So, this output restriction will automatically give me a restriction on the input if I want to look at this as a good linear amplifier. And therefore, let us try to recalculate what will be the maximum input voltages corresponding to plus 12 volts, let us say. You know that input voltage can be obtained as plus 12 volts divided by the open loop gain 10 power 5. So, plus or minus 12 volts divided by 10 power 5 gives me 120 microvolts. I have multiplied numerator denominator by 10 to make it 120 by 10 power 6 volts, and 1 by 10 power 6 is 10 power minus 6, that is nothing but microvolt. Therefore, what I get as the limits of the input voltages between the two input terminals is plus or minus 120 microvolt, as you can see. So, this is a maximum range of input voltages that I can give, for which the operational amplifier will perform like a normal amplifier. Output will be related to input by a factor which is called the open loop gain. If I give any voltage beyond this 1 plus or minus 120 microvolt, you would find the output will saturate at plus 12 volts or minus 12 volts depending upon the polarity of the input, right. So, if therefore, if I want to transform this into a graphical representation, how will it look like? You can see on the screen now I have shown I have the Vi on the x axis and the Vo on the y axis, because I can have both plus and minus, my axis also goes on both sides, plus side and the minus side. This corresponds to plus Vi and this side corresponds to minus Vi. Similarly, you have plus Vo and minus Vo. I also mark on that a 12 volts point, plus 12 volts and minus 12 volts for reference. Now, you can see if I start from 0 for my input voltage, this is Vi. So, if I keep increasing my input voltage slowly along the Vi axis, that means I have a power supply with which I can increase the voltage, and I apply between the two input terminals and keep increasing it, so that I get 10 microvolt, 20 microvolt, etc. And you would find till I come up to 120 microvolt, I can have almost linear behavior at the output. The output voltage also increases linearly, but the moment I go beyond plus 120 microvolt, you will find the output will remain at plus 12 volts for all input voltages which are larger than plus 120 microvolt. That is why you get a horizontal portion here. This corresponds to the saturation of the output. Similarly, when I look at the negative side, if I keep increasing my voltages on the negative side, minus 10 microvolt, minus 20 microvolt, etc., you would find till I reach a point corresponding to minus 120 microvolt, I will get linear behavior. The corresponding output will also be AOL into Vin, therefore it will also be negative, therefore it is shown on the bottom direction, which is the negative y direction, and you can see there is a linear relationship between the input and the output till I reach a minimum of minus 120 microvolt. Beyond minus 120 microvolt, you find the operational amplifier output saturates at minus 12 volts. This is what I already explained to you, and therefore the operational amplifier transfer characteristic will look exactly like what I have shown on the screen. There is a saturation up to minus 12 volts, and then there is a linear portion crossing through the origin, and again I have a saturation at plus 12 volts when I come from very deep minus voltages to very large plus voltages. This is the characteristic I will get. But you would find, I would perhaps explain to you, this has got very good applications, especially you can use non-linear applications of the operational amplifier are very useful. You can use amplifier in other applications where it is not the amplifying action which is going to be useful to us in different circuits, but this characteristic that it is able to distinguish between two voltages which are varying at the two input terminals within plus or minus 120 microvolt, then the output shows a sudden variation from anywhere between minus 12 volts to plus 12 volts or whatever, and therefore this variation switching at the output will be very useful for applications where the operational amplifier will not be a simple linear device, but it will become a non-linear device, and basically it is called a comparator. We will discuss in more detail about the behavior of the comparator, and we will discuss several other circuit configurations related to comparator. So, now I would take a small break and show you an actual demonstration where I will connect an input signal between the two input terminals of the operational amplifier, and we will observe the output Vo not by using a multimeter, but we will connect an oscilloscope, so that we will be able to sweep the input and the input voltage between two limits. For example, if I apply a sine wave input between with an amplitude of 1 volt, keeping the other input 0, then you would find with reference to the other input, this input will go plus 1 volt and minus 1 volt, and therefore we can see what happens to the output when this input is given. So, that will give us an idea of the transfer characteristics of the operational amplifier. So, you can see the circuit I have is a very simple operational amplifier, the same 741 with a 2 input. One of the input is grounded, is connected to the ground. To the other input I am connecting a variable sine wave oscillator, and the output is connected to the oscilloscope. So, the exact circuit is here, there are no resistors, you can see there are only 2 inputs and the output is monitored. Both the input and the output are connected to the x and y terminals of the oscilloscope. You have the 2 inputs x and y. I have used it in the xy mode. In every oscilloscope you have a selection in the sweep generator to put it into off condition. When you put it into off, then the 2 input terminals of the dual trace oscilloscope in general will become the x and y inputs of the oscilloscope, and therefore I have given the x from the input corresponding to the x axis and y corresponding to y axis I have given to the output, and this is the signal generator, the sine wave oscillator, basically from a function generator which can generate all types of waveforms, sine, triangular, square, etc., and we have put it in the sine, and these buttons are for choosing different frequencies. I have chosen something around 1 kilohertz, and therefore it is about 1.8 now. Using this knob I can vary the frequency, using this knob I can vary the amplitude, and the output is connected at the input of the operational amplifier. The pin number 2 is connected to the oscillator, pin number 3 is connected to ground as shown in the picture above, and the output pin number 6 is taken and connected to the oscilloscope output for the y, and one other extra terminal taken from the pin number 2 is given to the x input of the oscilloscope. Now I have a large amplitude, nearly about 1 volt or so here using this knob, and therefore with reference to the terminal 3, the terminal 2 voltage will go plus 1 volt to minus 1 volt or whatever, and therefore it will keep going up and down. Every time it goes up and down, it will certainly cross that 120 microvolt approximately, that what I mentioned. Therefore it will find beyond that 120 microvolt the output will become saturated at plus 12 volts or minus 12 volts as the case may be. What you see behind is actually the dual supply which is connected to the breadboard. So you can see on the oscilloscope screen the picture which I showed you just now. So you have a saturation here and you have a saturation here, and you have the corresponding slope, large slope. I did not mention to you that the slope, this is a linear portion of the amplifier, and if you calculate the slope of this line, vertical line, you would find that gives the open loop gain of the amplifier. So this gives us a method of measuring the open loop gain also, and you can see, I don't know whether you were able to see that, if you come close and have a look at this, you can see there is saturation here, there is saturation here, there are 2 lines here. I did not explain to you about 2 lines. Why do you get 2 lines here? It is very simple to understand, because when I come from here, the moment I cross this 120 microvolts, then it will go to the other end, and when I come from the below, it is a minus 120 microvolt at which I will make the transition, and therefore these 2 lines are corresponding to the 2 limits of that. And if I can look at the amplifier position, this is at 5 volts, therefore it is about 10 plus something, this also around 10. So it is around, if not plus 12 and minus 12, it is around 10.5 or 11 volts on either side. This is corresponding to minus 11, this is corresponding to plus 11, and you have the 2 lines corresponding to the 2 limits crossing the x axis at maybe plus or minus 120 microvolt. So this is exactly the same as what I explained to you as corresponding to the transfer characteristics, and the slope of this line, if you expand the axis and measure, you can measure the slope by knowing what is delta t and the delta v. If you divide the delta t by delta v, you will get a number which is actually corresponding to the open loop gain of the amplifier. So having seen the transfer characteristics of the operational amplifier using an oscilloscope, where you can see the two saturation regions corresponding to the output, and then you have the two transitions corresponding to the open loop gain when the two voltages are very very small. We have seen that. Now let us move on to the next characteristic, which is called the gain bandwidth product. Every amplifier has got a gain factor. We all know that gain is basically the magnification factor. So when I apply an input, I get an output which is larger in magnitude corresponding to the input, and then only we call that as an amplifier. It amplifies the signal, input signal. So this amplifier gain plus another feature of any amplifier is that the amplifier cannot be having the same gain throughout for all different frequencies that I give at the input. As I change the frequency at the input, you would find the gain can change. In principle, an ideal amplifier, if I take, you would expect the amplifier gain should be a constant for all frequencies of the input. But in reality, we have already seen when we discussed about transistor amplifiers that because of the several capacitances that are used in the amplifiers, you would find there will always be a lower cutoff and an upper cutoff in frequency, beyond which the amplifier will not have a stable gain. So this difference in the two frequencies, the lower cutoff and the upper cutoff, is what is commonly known as bandwidth of the amplifier. So in the case of an operational amplifier, we all know basically there are no capacitors in general in the design of this operational amplifier. There is only one capacitor. For example, in the case of 741, when it is designed using the silicon chip, it is all an integrated circuit. That one capacitor is meant to make the output gain fall at a steady rate, and that is the reason why that capacitor is introduced into the design, and that is around 30 picofarad is the actual value of the capacitor. So there are no capacitors as such at the input side, and therefore you would find it can amplify even DC signals, which corresponds to 0 frequency. Therefore the lower cutoff for the 741 or any operational amplifier, DC coupled differential amplifier, is 0 frequency, that means DC. But you will always have an upper cutoff corresponding to the capacitor that we have introduced, as I mentioned already, the 30 PF. So you would find the gain will start rolling down, rolling off at the output at a steady rate, and that will decide what is the bandwidth of the amplifier. But the point that I am trying to tell you here is that the product of the gain and the bandwidth for an amplifier is generally a constant. That means if I have small gain, that amplifier can have large bandwidth. If I have large gain, then that amplifier will have only a small bandwidth. So there is a trade off now. If I want good bandwidth, then I should try to keep the gain of the amplifier low enough. If I want very good gain, then I must make sure that I do not look for the large bandwidth. It cannot happen because the product is a constant. So that is what we call the gain bandwidth product. Now in the case of operational amplifier, you can see on the screen I have shown a Bode plot. What you see on the screen, the graph, is called a Bode plot. You have on the x axis logarithm of frequency, and you have on the y axis the gain, and this gain also is in logarithmic scale. That means there is 1 here starting at the bottom, then you have 10, 100 to 1000, 10,000, etc. It goes in logarithmic scale, and similarly in the x axis I have 0 frequency, then I have 1 hertz, 10 hertz, 100 hertz, 1 kilohertz, etc. So this is also logarithmic scale, this is also logarithmic scale, then this is called Bode plot. And if you look at that, AVO, that is, this is the open loop gain. This point should approximately correspond to 10 power of 5 for the case of 741, because that is the magnitude of the maximum gain that I have at 0 frequency, and this is 10 power 5. But you can see the 10 power 5 immediately after short distance it is constant. Beyond that you find it is rolling off, it is coming down on a very steady way, and this is corresponding to the roll of the 30 pf capacitor that I already mentioned to you. And so this is a roll off, and you find if I want to measure bandwidth, the bandwidth is generally defined. Well, how do you define the cutoff frequency for knowing the bandwidth? I should know what is the cutoff frequency. The cutoff frequency is not the knee portion where it starts bending, it is actually the point where if it is an voltage amplifier, the voltage gain becomes 0.707 times the mid frequency gain. This maximum gain multiplied by 0.707, that will wherever is that gain is achieved, that point, that frequency on the x axis will correspond to the upper cutoff. This I explained to you when I discussed about the frequency response of transistors and amplifiers. You would remember it comes because of the power coming down by half the value corresponding to the maximum gain. Power half means voltage gain. In terms of voltage gain, it will become 1 by root 2, and the value of 1 by root 2 is 0.707, 1 by 1.414. So that is the reason why you have here a lower cutoff corresponding to 0.707 times the mid frequency gain, and that point is the cutoff frequency corresponding to the high frequency. Now this is the cutoff point corresponding to open loop gain. So this will be about maybe about 10 or 10 hertz or something like that. But if you now reduce the gain, instead of 10 power 5 you can get very high bandwidth. I already mentioned to you the gain bandwidth product is a constant. Therefore what is shown in the graph is corresponding to a gain 1 when the output is equal to input, the gain factor is 1, then you would find I will get a cutoff frequency almost corresponding to 10 power 6, this f1 corresponding to the b1 is 10 power 6. Therefore the amplifier has got a bandwidth of 10 power 6. So it can amplify up to 1 megahertz of frequencies at the input if I compromise and decide to have the gain of the amplifier unity, right. So this will now give us a number corresponding to the product gain bandwidth, because f1 is nothing but the differential gain multiplied by the cutoff frequency. The cutoff frequency in this case is 10 power 6, and the differential gain I already mentioned to you is unity. Therefore 1 multiplied by 10 power 6 is nothing but the gain bandwidth product, and that is 10 power 6. So once I know what is the gain bandwidth product for a given operational amplifier, then I can immediately see this second graph shows you all the things. If I want a gain of 10, what will be the bandwidth? I can quickly calculate, because the product of gain and bandwidth is a constant, and that is in this case is equal to 10 power 6. So if I have the gain of 10, the bandwidth should be 10 power 5. That means it can only amplify up to 100 kilohertz frequencies. If I make my gain 100, then you can immediately imagine the cutoff frequency will be around 10 power 4, that corresponds to 10 kilohertz, and that is what is shown in this graph. For 100 it comes at an earlier point in the frequency, at 10 it comes at a later point, and at 1 it almost goes to the point where the graph touches the x axis. This corresponds to 10 power 6, this will correspond to 10 power 5, this will correspond to 10 power 4, etc. So you can see as I keep increasing the gain, the bandwidth keep decreasing, because the gain bandwidth product is a constant. Now how do we get the gain bandwidth constant? How do we get? The simplest method I also mentioned to you is to make an amplifier with a gain of 1 and apply different frequencies at the input, find out where the input output voltage decreases from the constant value to 0.7 times the maximum value, and at that time whatever is the frequency that gives you the cutoff frequency for the output, and that in this case when a gain is unity gives you the gain bandwidth product directly. So now we have just taken an example, numerical example. Calculate the cutoff frequency of an op amp having specified values of B1 equal to 1 megahertz. That means unity gain bandwidth product is 1 megahertz, and the differential gain is given as 200 volts per millivolt. That means what? If I apply 1 millivolt at the input, I will get 200 volts at the output. That is a gain factor. So this is not true in reality. We have already seen there is a maximum with reference to plus 12 and minus 12 volts, all those things, but this is an expression of the gain ratio, that is all. So we know now that the gain bandwidth product is 1 megahertz, and they have given the gain as 200 volt divided by millivolt, and therefore the cutoff frequency is nothing but the gain bandwidth product divided by the gain, and in this case 1 megahertz is the product divided by 200 volts divided by millivolts. That millivolts will become 10 power 3 when it goes to the numerator. So you would find when I look at that it comes to 5 hertz. So when I have large, this corresponds to a large gain, 2 into 10 power 5, and therefore this is here 2 into 10 power 5 is the gain factor in this case, and therefore the bandwidth will be very small. When the gain is very large, the bandwidth should be very small, and the bandwidth is only 5 hertz. So this is a typical example to show you that when I have large gain, the bandwidth will become very small. Now I want to show you a demonstration with 2 circuits having 2 different gains, and we will try to find out how the gain is changing with how the bandwidth is changing when I increase the gain. That is what I wanted to show you. So for example, the first circuit you would find has got 10K and 10K. These are all inverting amplifiers, as you can quickly recognize. You have RF and RI, both are 10 kilo ohms, and the pin number 3 is grounded. There is no input with a 10K to compensate for the input bias current variations, about which we have already seen. The output is seen on an oscilloscope, and the input is from a signal source, sine wave oscillator, whose frequency can be varied up to several megahertz. So if the operational amplifier has got a gain bandwidth product of 10 power 6, I assume G, the gain into bandwidth, is equal to 10 power 6. Now what I am going to do is, the gain in this case is 10K and 10K, the ratio of RF by RI is 1, and therefore the gain is 1 for this circuit. So when the gain is 1, the bandwidth B is 10 power 6 hertz. So you would find when till I go to nearly 1 megahertz, you would find the output amplitude will not change, it will almost remain constant. When I have in the second circuit, what I have done is, in the feedback, instead of using 10 kilo ohm, we have used 100 kilo ohm. That means what is the gain in this case? It is 100 divided by 10, and which is 10. So the gain is now increased by 1 order of magnitude from unity to 10. So when the gain is 10, then the bandwidth becomes 10 power 5 hertz, that corresponds to 100 kilohertz. So you can see previously for the unity gain the bandwidth was 10 power 6. When I increase by 1 order my gain, the bandwidth decreases by the same 1 order, and it becomes, instead of 10 power 6, 10 power 5 hertz. Therefore this will clearly bring out, I suppose, that the gain bandwidth product is a constant. So I want to take these 2 example circuits and show it to you. You can also try in the lab by increasing the gain to 100, and then you would find it corresponds to 10 power 4, etc. You can keep trying that, but it is, I already mentioned to you, if you have very large gains, it becomes very difficult to stabilize the amplifier due to several other noise input and things like that. Therefore it is always advisable to go, not to go beyond 100 or so in the gain of the amplifier. because you also know the lower the gain. How do you lower the gain? The only way you can lower the gain is by giving feedback, and that is negative feedback. And once you give negative feedback, we already seen when we discussed about negative feedback that you have lot of good things happening to the amplifier when you give negative feedback. The input resistance increases, the output resistance decreases, the bandwidth increases, distortion decreases, etc., and they are all by the value of gain that you have sacrificed. Instead of 10 power 6, which is the open loop gain, if I do only 10, I have sacrificed a factor of nearly 5, 10 power 5, and therefore you would find all the characteristics of the amplifier improve by a factor 10 power 5, and therefore in that sense also we should not design amplifiers which are having very large gains, then it will become very difficult to handle. So with this, let me go to the table and show you a demonstration of the two amplifier, one with a gain unity and another with a gain of 10. Both I will apply the signal and try to observe what happens to the output. I will show you that the output starts increasing at a particular frequency. I will almost take that as nearly the cutoff frequency. Otherwise one has to carefully look at the output and calculate when it becomes 0.70 times the mid frequency gain, and that will be the point to precisely choose. In general what we will do is we will take lot of data in the lab and then draw a graph in the log plot, and you will try to find out exactly the location where the value of the gain becomes 0.7 times the mid frequency gain. Here I will just indicate to you qualitatively that beyond that FC the amplitude starts coming down, so that will help you to identify the bandwidth of the two amplifiers. So we have again the breadboard with the two circuits simultaneously shown. This circuit has got a 10k in the feedback and 10k at the input. RF by Ri is equal to 1. So this is an inverting amplifier with a gain of 1, and that circuit is shown here at the bottom in the breadboard, and the input is connected from the signal generator, which is again the sine wave oscillator. You have the amplitude variation here and you have the frequency variation here, you have got frequency multipliers here, and I have used the sine input here. So this signal generator is connected to the input and the output is connected to an oscilloscope, which you can see here, and it is a dual trace oscilloscope. The top one is corresponding to the input and the bottom one is corresponding to the output. The two are connected here. Now what I am going to do is I am going to vary the frequency of the input, I am going to vary this knob, the frequency of the output, and I will ask you to observe the oscilloscope output carefully. You see the oscilloscope output, can you see the oscilloscope output? You see when I keep increasing, you can see the frequency increasing, but the amplitude of the output is almost a constant. The amplitude of the output is constant, both the input and the output is constant till I complete the entire range of frequencies using this knob. Now what I am going to do is I have almost come to the end of this, and the frequency also has increased. Now I will go to the next multiplier. So I will bring down to the original value and go to the next level of frequency, which is now it is in 10k. Now I go into 100k. I press the 100k. Now let us see. You can see the two signals, they are very close. So now let me increase the sweep frequency, so that again I am able to see few of the waveforms. And now what I am going to do, again increase in 100 kilohertz range my frequency, my input frequency. So we are still having, now only it starts decreasing slowly when I am almost at 300 kilohertz and things like that. So if I now go to higher frequency like 1 megahertz, you can see almost the output is decreased in amplitude. So when this decrease starts is what we should worry about, and we would be that will correspond to when it comes to, for example, this is what the minimum around 200 you would find is already less compared to the input, less than what you had previously, because the gain is 1 but they must have the same amplitude in principle. But you can see the bottom signal is having lower amplitude than the top, and so this happens when I press and go into the 1 megahertz, several other hundreds of kilohertz away it starts decreasing, and we can precisely calculate from the amplitude when it becomes 0.7, and you would find it will be very close to 1 megahertz, because the gain bandwidth product for the 741 is very close to 10 power 6. So this is corresponding to the gain of 1 in the circuit that I have shown. You can see this is the circuit that I have now used with a gain of 1. Now what I am going to do is I am going to connect the other amplifier. Now you can see it is around the 10 kilohertz range, it is around 5 kilohertz, and in the oscilloscope you see the 2 amplitudes, and if you actually come and look at these dials you would find they will be 10 times, this will be around 0.5, this will be around 5. So you can see there is a gain of 10 shown. The amplitude here is almost equal because the amplification factor using the knob has been kept 10 times, that takes care of the gain of 10, because here in the feedback I have used 100k, and 100k divided by 10k gives me a factor of 10, that is a gain of this amplifier. Now the same amplifier is shown here, except that this resistance which was previously 10k now I have changed to 100k. Now the 2 inputs are given as usual, and let me now vary the frequency and see how the amplitude is changing. So I am changing now in 10 kilo. See, when I go through the entire range there is no significant change in the amplitudes of both. I will again change the sweep to see few waves, and I am going up to the extreme end of the knob. You find there is not much of a change in the amplitude. Now I will quickly come back and increase the multiplier, frequency multiplier, to 100k range. Now I am going to increase in the 100k range. Now you would find as soon as I do that the gain starts decreasing. Now you can see that the gain here has started decreasing. Now it is more, I come back, now it is nearly 1 centimeter, 1 division on the screen. Now as I increase the frequency you find the amplitude starts decreasing. So this corresponds to the cutoff, very close to the cutoff, and this comes in the 100 kilohertz range, nearly about 200 kilohertz or so. Previously it was coming, when I used gain of 1 it was happening till 700 800 k, you had no fall in the gain, but now you do get a gain much lower frequency, and therefore the gain bandwidth product makes that when you increase the gain the bandwidth decreases. Now the bandwidth in this case has decreased, so we can continue and try to do for a gain of 100. Then what will happen is you must make sure that amplitude of the output will be very very large, therefore you should correspondingly reduce the input signal so that you can still have reasonable amplitudes of the 2 signals on the oscilloscope. I leave that for you to try on your own. So we have seen now a demo of the gain bandwidth product, how it is a constant for 2 situations, where one you have an amplifier with a gain of unity, and when you locate the exact cutoff corresponding to this amplifier, that will give you the gain bandwidth product. Then we also chose another amplifier with a gain of 10, and then we looked at the bandwidth. You would find it, even when I come to nearly 100 kilohertz, you would find the gain starts falling. That means the output amplitude start decreasing, that corresponds to the gain falling, and therefore that shows that the gain bandwidth product is a constant. Now we go to the last of the characteristics, which is called slew rate. Slew rate is a very important characteristics, especially when you want to look at large amplitude signals at the input. When you give a large amplitude signal, you expect the output signal also should be quickly changing, but you would find it is not happening that way. So, a factor or a characteristic of the amplifier which identifies this variation, how fast the output changes with reference to time corresponding to the input change, is what is known as slew rate, SR. Slew rate, therefore, you can see on the screen, is defined as the maximum rate at which the amplifier output can change in volts per microsecond. The unit is generally volts per microsecond. So, slew rate is delta V naught, that is a change in the output voltage, divided by delta T, where delta T is measured in microseconds, delta V naught is measured in volts. This provides how fast the output can vary corresponding to a input change. One way to look at is to look at a step input. So, I have shown in the graph, for example, I give suddenly a 1 volt jump at the input. The input goes from 0 to 1 volt, and what happens to the output? You would find, in principle, you expect the output also should go from 0 to 1 volt immediately. There is nothing like immediately, right? The output will take some time to react to the input, and that time is what will be decided by the slew rate of the amplifier. So, you can see here, this is corresponding to the input, this is corresponding to the output. When the input goes from 0 to 1 volt, the output goes not immediately, but with a finite slope to the value 1 volt. So, the x axis is in microseconds time and y axis in volts. So, this 1 volt divided by this time, which is here 0.5 microsecond, gives me the slew rate of the amplifier. So, that is the way we can measure. I will again explain to you with the actual square wave. So, if I give a large amplitude square wave 1 volt or 2 volts and look at the output will show a finite slope. And if I now look at how much is the variation in the amplitude at the output variation, and look at that time it takes for this value to reach the maximum, and divide one by the other, I will get the slew rate, delta V by delta T, where delta V is in volts and delta T is microsecond, gives me the slew rate. This is a very simple way of measuring slew rate, and I will give you an example, a numerical example for an op amp having a slew rate of 2 volts per microsecond. This is a very typical value of the slew rate for many of the operational amplifier. What is the maximum closed loop voltage gain that can be used when the input signal is 0.5 volts in 10 microsecond? Therefore, you can see that this slew rate can introduce a restriction on the gain that I can have, not only the bandwidth. This is because slew rate also indirectly related to the bandwidth, the rise time and things like that. So, you would find if V naught is equal to A closed loop multiplied by Vi, and delta V naught by delta T is equal to the, I am just dividing both sides by differentiating actually, delta V naught by delta T is equal to ACL into delta Vi by delta T. Therefore, ACL, the closed loop gain, can be taken as delta V naught by delta T by delta Vi by delta T, and if that is delta V naught by delta T is what we call the slew rate, and therefore it is slew rate divided by delta Vi by delta T. In the problem they have said it is 0.5 volts per 10 microsecond at the input, therefore I put it at the denominator. 2 volts per microsecond is a slew rate, I put at the numerator, and if I calculate this, the gain is to be 40. That means I cannot design using this operational amplifier which has got a slew rate of 2 volts per microsecond any gain greater than 40. That is what it means. Therefore, this puts a restriction on the gain that I can achieve for a given amplitude of the input voltage. So, I want to, if you want to measure the slew rate of operational amplifier, it is a very simple circuit I have shown on the screen. You have a gain 1 amplifier 10k and 10k, there is this thing, it is an inverting amplifier. I give a square wave, and at the output I will get a distorted square wave with some slope, finite slope, and I will calculate directly from the oscilloscope what is the time corresponding to this delta t and the amplitude. Therefore, if I divide one by the other, I will get the slew rate. Therefore, it is possible. I have given a small example here. R1 and R2 are 10k each, these are all in kilo ohms, and input voltage is around 2 volts. Output voltage also is 2 volts because the gain is 1, and input frequency is around 120 kilohertz, and time taken to switch from minimum to maximum is 1 microsecond. This is delta t, and therefore the slew rate is 2 volts divided by 1 microsecond, that is 2 volt per microsecond is a slew rate. So now I will show you a demo of this slew rate quickly. So I have the same circuit here with the 2 resistors, all both of them equal to 10 kilo ohm. Therefore, it is a unity gain inverting amplifier. I have got an input, and that is now in square wave in this sine wave function generator. You can see I have pressed the square wave knob, and therefore it is giving out square wave. It is around 26 kilohertz is the frequency corresponding to this knob. And now I will see what is the output. You can see on the oscilloscope, this is the input square wave where the vertical line is almost not seen because it is at the input, whereas because of the slew rate at the output there is a finite slope. So you can see the sloping lines. If I now increase the gain, you will be able to see it much better, you will be able to see the variation much better. So you can see that this is not instantaneously going to high, but with a finite slope. Now if I calculate what is the gap here from the microsecond that I can read from here, and from the amplifier gain factor, I can find out what is the amplitude here. Divide the amplitude by this delta t, which is read from the oscilloscope, you can get the slew rate, and in this case if you actually take a close look at this, you would find it comes to around 2 microsecond. So this corresponds to the slew rate of the operational amplifier. So we also saw a demonstration of how to measure the slew rate of an operational amplifier by taking an example of a unity gain amplifier. I give a square wave and monitor the square wave using an oscilloscope at the output and calculate from the slope the slew rate. So far what we have done is we have listed the different characteristics of the operational amplifier, and we have discussed the basic definition of the characteristics, and we have also seen how we can measure this characteristic in the actual laboratory. So I want you to recapitulate at the end that you have the different input offset voltage, input bias current, input resistance, output resistance, common mode rejection ratio, the transfer characteristics between the input output of the amplifier, the gain bandwidth product of the operational amplifier, and the slew rate. All these characteristics are the most important characteristics of the operational amplifier. One should have a good idea about these amplifiers if you want to make use of these operational amplifier for different application purposes. For example, when I want to amplify some small currents, I must make sure the input bias current of the operational amplifier itself is not close to the current that I want to measure in a current to voltage converter configuration. So I must make sure that the input bias current is at least 1/10 or even lower than the order of magnitude of the current that I want to measure. Similarly, when I want input voltages which are in microvolts, I must make sure the offset voltages of the operational amplifier are much lower than that. It should be in the nano or pico volts range, and therefore I must make a careful selection of the operational amplifier whose input offset voltage and output offset voltage are very small compared to the order of magnitude of the voltages that I would like to measure in my actual application. So for such considerations, it is very important that we have very clear idea about the different characteristics of the operational amplifier and how one can measure them in the actual laboratory. in the next lecture perhaps we will take up some application circuits of the operational amplifier. We have seen about the negative feedback and the various configurations of the negative feedback, and then we have discussed about the mathematical operations that can be performed with the operational amplifier, and we have also seen the different characteristics of the operational amplifier. Now we are ready to go into different application circuits of the operational amplifier. Thank you.